All right, 5.6, multiplying polynomials. So yeah, we did see some addition and subtraction of polynomials. And remember, addition of polynomials is really just combining like terms. Subtraction of polynomials, just like we saw in that example, is to distribute a -1 into the parentheses, which really is just changing the signs of all the terms on the inside, and then combining like terms. But now multiplying polynomials. So it's helpful usually to look back here at some of our rules for exponents. Really, the one that we're going to be focusing on is usually the product rule, because we're going to see like bases be multiplied, and then we can just work with those exponents, okay? We're not usually dividing them, or even, we may see some exponents of 0, that's possible, or even some negative exponents or something like that, but probably not too much. It's most everything we're going to be doing is held within the product rule. And this goes back to the idea, if we just can remember that distribution is multiplication, then we can see, well, we'd be multiplying the same bases. All you got to do then is to add the exponents right there. Now, everything out in front, the coefficients, they'll be multiplied. We can multiply the numbers, but if we, like this, we're usually looking at this with x's, right? So if I said x to the power of 2 times x to the power of 3, well, you could expand this and say 2x's multiplied by 3x's like this, which would show you it's x to the power of 5. Or you could say, well, x to the power of 2 plus 3, which is also x to the power of 5. Now, we're not going to be expanding these like this, but just as a quick review, that's what's happening. We're just taking a little bit of a shortcut by adding those exponents, okay? But this is only when the bases are variables or letters like this. That's it. If they were numbers, then we would just multiply them. This one, and some students look at this like, hey, there's no distribution. Well, distribution is multiplication, and as far as I can tell, that's multiplication right there. So that means this is distribution. It's just, you know, one rainbow, if you want to show the rainbow. But that's completely up to you. Now, like I said, we multiply the two coefficients together. So I'd start with 9 times 3, which is 27, okay? On the other hand, we have the x's, which we will also multiply, so that'd be like x times x to the power of 4. And this is where we've talked about before, where it may be useful for you to see that power of 1 until you can get used to knowing that it's there. Maybe you just want to show it, okay? So then we would say the bases are the same, the x's bases, and then we're going to take those two exponents and add them together. So that would be then x to the power of 5. Now, well, this is fully simplified. Now this means we also could have went back here at the beginning and said, you know, it's just multiplication, right? So technically speaking, we could have said, I really don't care if there's parentheses there or not. It's just straight multiplication, okay? Now that's distribution of one term into another term. It's like, it's kind of like saying we're multiplying two monomials together. So another common mistake we see on this one is where students would get an answer like this. Okay, and I think you'll understand where it comes from. They'll get 12x to the power of 5. Okay, now the x to the power of 5 is good, like we see in the actual answer right there. But what they've done is they've applied the exponent rule to the coefficients. Okay, 9 plus 3 is 12. But remember, it is still multiplication, so that's why we've got to multiply those. Just be aware of that common error that we see. Don't try to avoid that if you can. But it's possible to distribute like this one right here, a monomial into a, trinomial or any kind of nomial, polynomial. And for the most part, we've just seen it like this, right? And then you say, hey, I'm going to distribute the 5 like that. But now we're saying, look, there's more to the 5 than what we've been seeing. We can start tacking on variables like that, okay? X to the power of 4. And again, the power of that x really is not so important. If that 5 was to some power, we would probably evaluate that. But for the most part, we should only see the variables with the exponents like we're seeing here. And again, the size of this exponent, all it does is change the amount of work that we have to do, but it's not like it's more difficult work than what we've been seeing, okay? Whether you understand it or not, by the way, because if you're not understanding it, then it's the same amount of work. If you're understanding it, it's still the same amount of work, okay? So here's what we're going to do, distribute, okay? So, that's kind of bigger than I wanted. There we go. So that's 5 x to the power of 4 times 8 x to the power of 2. So we'll write this out, 5 times x to the power of 4 times 8 x to the power of 2. Okay, well, now I know 5 times 8 is 40. And then my x to the power of 4 and my x to the power of 2, they'd be multiplied, so I'm going to skip kind of a little bit of work there and just show that we would then be adding those exponents, okay? So then that becomes x to the power of 6. Well, then we have this other distribution here, okay? So it's the same 5x to the power of 4, it's just now being multiplied by this 4x term. Okay, so once again, I split these up. The coefficients, 5 times 4 is 20. It's positive 20, so I'll show that as plus 20. And then I got my x. My x is on this x to the power of 4, and then that's an x to the power of 1. So that's 4 plus 1. That would be x to the power of 5. And then this final distribution to the negative 2, well, 5x to the power of 4 times negative 2. So the numbers, 5 and negative 2, I'm going to multiply those to get negative 10. And then that x to the power of 4, it has no other x's to multiply with, so it just comes out as an x to the power of 4. So the more experience you get with this stuff, you'll see eventually you'll just be like, I see the x's are the same, just 4 plus 2 is 6, 4 plus 1 is 5, and then there was no x's with this too, so x to the power of 4 just kind of drops with this one. However you want to look at it, I do hope the color coding helps. And I would just kind of leave it in this order based on this second set of parentheses right there. Right? Like this first red term was based on the 8x to the power of 2. The 20x to the power of 5 is based on the 4x. And then the negative 10x to the power of 4 is based on the negative 2. Everything was affected, though, by this 5x to the power of 4 after it was distributed. And I just can't emphasize this enough. Distribution is multiplication. As long as you can understand that, then hopefully this makes more sense. Well, that's a monomial multiplied by any polynomial, monomial, binomial, trinomial, okay? But what we're going to start seeing is usually it's a binomial multiplied by some other polynomial, okay? So that instead of that first term, which on that last problem was 5x to the power of 4, it's going to be like x plus 3. That's in parentheses, okay? And I think you've seen something like this before. Generally speaking, like I said, mathematically, we usually look at these in binomials. So you could say like x minus 3 and x plus 2. And then we got two binomials that we're going to be multiplying. Okay, so distribute each term in the first to the second. We're talking about the polynomials. Now, if you need to expand with the exponents like we've seen, right, where we did x to the power of 2 times x to the power of 3, you can expand those exponents, but like I said, we're going to be taking the shortcut of, if we need to, just adding the exponents for the variables, okay? And yeah, from time to time, that you'll see that some terms will zero out because they just cancel out with other like terms. By cancel out, I mean zero out, right? And then essentially we make that a phantom zero, and then we just don't have to look at it anymore. And so you may end up with even less terms perhaps than what you may have expected in the beginning. All right, let me kind of expand on this. Okay, so let's look at this example that I have on here. X minus 3, and then that's one binomial, and then the other binomial is x plus 2, okay? Now, what this is it's factoring, just it's backwards from factoring. Multiplication is kind of backwards of factoring. Distribution is backwards from factoring. So here's what this is, okay? This first term in the first binomial, x, it's like saying you're going to take that x and multiply it by the second polynomial. This one's just a binomial, but it could be a trinomial, okay? And then what you're going to do is you're going to take the second term, the negative 3, and you're going to multiply it also by the same second binomial like this. So what we end up with is two sets of distribution. It's just kind of shown in a different way. So, you know, I guess we use some rainbows because they're so pretty. Some people like to show it like this, and then this one like this, okay? For two binomials, this is also known as FOIL, which we'll talk about. I don't care for FOIL, though, because, I don't know, it's kind of a gimmick. But if you can just understand that all you're doing is taking one polynomial, and each term is multiplied by the second polynomial every time, then FOIL, I would kind of hope you'd forget about FOIL, okay? So this is what this means with that backwards distribution stuff, okay, the factoring. is, see how there's a factor for both these. This is two terms, by the way. You got this term, x plus 2, and in this term, you also have a multiplied by x plus 2. It's like saying we're gonna factor these out into just right here, okay? Well, then what are you left with? You got the x minus 3, and that would become its own binomial. That doesn't have to make a lot of sense now, but later on, if you end up taking like 1010 or 1050, I hope that that will help. So here we go. Here's our first one. We're gonna multiply these two, okay? So I'm going to take that first term, this x term, and I'm just going to multiply it by the second binomial here. Now, once again, just don't worry if this was a monomial, if this was a trinomial, or some kind of giant polynomial, it would still be the same. Whatever's in there would be in the same parentheses here. Okay. Now I'm going to take the positive 6 here. Now I'll even show it as plus 6 right here. And I'm going to multiply it by the other binomial. And this sets up what will end up being as, I guess it will end up with 4 terms, but then we'll see if there's any combining of like terms that's possible. If there is, then we'll do that, and then it'll be considered simplified, okay? So I'll start with the x. So that'd be x groups of 2 x's. Well, that's a coefficient of 2 with x's, but 2 of those x's. And yeah, if you needed to see those ones there to add those exponents, that's fine. And then I'm going to distribute the x into the negative 4, which I prefer to show with the coefficient in front, negative 4 times x. Okay. Then the positive 6 will distribute into, it's the same binomial, just shown separately here. So that's 6 groups of 2 x's, which would be positive 12 x's. And then 6 groups of negative 4, which would be negative 24. Okay? So we did some distribution there, double distribution, although, I mean, eventually it could be triple distribution. It could be. But now what I see from this new expression here at the bottom is that I got these two x terms right there. And they just happen to be right next to each other. But that means that I can combine those. How many x's would that be? Negative 4 plus 12 would be positive 8 x's. So I'm going to take my 2x to the power of 2, and I'll combine that with the expression, and also my negative 24. Those just get dropped, and that's it. That now is fully simplified. There's no other like terms to combine, nothing to distribute. I mean, you could say, well, we could factor, but I think that's for a different module. Oh, there we go. See, now we got a binomial multiplied by a trinomial. And again, this is where FOIL essentially breaks down because we got more than 2 terms in one of the parentheses, okay? So, same idea though. It's just, yeah, we're gonna end up with more terms in the end, but I'm gonna take my 4x here, and I'm gonna multiply it by that second set of parentheses. I'll take a little bit of a shortcut. Hopefully that's okay. So I'm gonna multiply that 4x by that second set of parentheses, and then I'm gonna take that plus 4 there, the other part of that binomial, and I'm going to multiply it also by the same trinomial, okay? And random space, that's okay. So now I know when I'm multiplying each, that trinomial by both times. And let's go ahead and start that distribution, okay? So I got 4x times x to the power of 2. Maybe we can see that exponent, but that'd be 4x to the power of 1 plus 2, which is now 3. So 4 times x to the power of 3. And then we got to distribute to the 3x, so that's 4 x's multiplied by 3 x's. So 4 times 3 would be positive 12. And then x times x would be x to the power of 2. Okay. And again, if you need to add those exponents that are phantom ones, that's fine. Now the 4x gets distributed to this negative 2. That's multiplied. And 4 times negative 2 would be negative 8. That's how many x's we would have there. And that's all 3 distributions of that 4x. But then we got the plus 4 in purple, which we also have to distribute. So 4 times, if you need to see that phantom one, that's fine. But 4 groups of x to the power of 2. And it's just positive 4 x to the power of 2. And some of you can see that already just from that 4x to the power of 2, we already have a like term that we will end up combining with. But before we do that, let's finish the distribution, okay? So then we got 4 groups of 3 x's, which would be positive 4 times 3 is 12. That's how many x's. And then finally 4 groups of negative 2, which is negative 8. Okay, so we get 6 terms because we distributed into a trinomial 2 times. And now we just look for any like terms to combine. And yeah, like I said, we got the x to the power of 2's right there. How many x to the power of 2's would that be? 12 plus 4 is 16. That's positive, so plus. But I also have the regular x terms, negative 8 of them and 12 of them, which result in positive 4 of the x's. So I'm going to take that 4x to the power of 3. There was no other like terms to combine with it. And also the negative 8, nothing to combine with it. And so the nice thing about this, just the way that it was set up originally, is it resulted in our final polynomial, which is already in descending order. Now, would it matter what order you put this in on the homework? I don't think it will, but I've been wrong before. But FOIL, okay? So I really don't like FOIL. It does stand, what do they call those, an acronym? So it's first, outer, inner, last. And the reason why I don't like it is because it's not always applicable. Okay, like on that last problem we just barely did, we multiplied a binomial by a trinomial. Well, what happened to FOIL? It's garbage. Okay, because this will only give you 4 terms. We ended up with, what, we ended up with 6 terms or something like that after the multiplication. Of course, it simplified it into 4 terms, but that's different. Okay, so I really don't care for FOIL, just as long as you remember that you're distributing terms from the first polynomial into the second one. You don't really need FOIL. If it does help, that's fine. First, outer, inner, last. So I'll take that back. But some students do benefit from this. So here's what this means. Okay, you got let's hope plus signs to make this kind of easy to recognize. And we can even use letters X, Y, Z. I guess I should have done W. All right. So firsts means that you're going to multiply the first terms, x and z, and then the outer terms, that would be x. See how x and w are on the outer edges of the 2 binomials. And then you'd say, well, now you got your inner terms, that'd be y and z, and then lasts would be y and w. You just multiply those, and then whatever you get, and then if you can combine stuff, then you do. If you can't, then you don't. Like I said, the moment that you take this and and you say plus a right here, then it screws things up, and people feel bad inside. Okay, so I don't care for FOIL. If it helps you, use it, but I'm pretty much not going to be using it at all. Okay. By the way, if you use it, it's not like you're going to lose credit on anything. I'm just saying I prefer not to because it goes away pretty quick unless you're using binomials like this problem just happens to be. Okay, so 5x minus 9 times 5x plus 9. So like I said, I would take the first term here, 5x. And by the way, for those of you that are like, I already know what's going to happen on this, that's great, but we don't have those rules yet, so I'm going to skip it. Okay, so I'm going to just multiply that 5x by the second binomial, and then the negative 9, I'm also going to multiply by that second binomial. Okay, and then I'm just looking for some distribution. That's it. So 5x's times 5x's. So 5 times 5 would be 25, and then x times x, that'd be x to the power of 2. Again, if you need to see those exponents and add them, then do it, okay? And then we got 5x times 9. So 5 times 9 would be positive 45, and then there's only the one x there, so just keep it. Okay, well, negative 9 times 5x's. Okay, well, that'd be negative 45x's. And then negative 9 times 9, it's positive 9, that'd be negative 81. Well, we do have these set of x's inside that we can combine. The problem with this is how many x's will that be? It's 0 x's. So we got 25x to the power of 2. You could say plus x to the 0x to the, well, sorry, 0 times x. And then minus the 81. But like I said, we usually just make those, I wouldn't put that in the canvas. I think that would even mark that incorrect. So to clean this up just a little bit, really just move them closer together. 25x to the power of 2 minus 81. And like I said, it's kind of a, some of you may have known that shortcut right there where the 2 inner terms were going to cancel out. If you knew that, that's fine. You know, you're not going to lose credit if you know that. But most students don't at this point because we don't have enough experience with this stuff. All right, now, again, since we're getting used to this, sometimes this can cause some confusion as to what is actually happening right here. It's 4w minus 8 to the power of 2. So all we're going to do is take that 4w minus 8, and let's just expand that, right, which I think we saw in that one slide. And so we're just multiplying this by itself, okay? And there is a rule for this one, but again, if you can just understand that it's polynomial multiplication, then you'll be in good shape. So I'm going to take this 4w, and I'll multiply it by that second polynomial there. And then I'm going to take my negative 8 and multiply it also by that second polynomial. Okay. Well, now that we have this, well, we're looking for some distribution. So 4w's times 4w's. 4 times 4 is 16, and w times w, that's w squared. And then 4w's times negative 8. That'd be 4 times negative 8 is negative 32. That's how many w's you'd have there. And then negative 8 times 4w's, and you'll see kind of a repeating theme here. But negative 8 times 4 is negative 32 w's. And then negative 8 times negative 8 is positive 64. Okay? So now we look for any like terms that we can combine, and we got the w's there. These are not opposites like that last problem. So it's like negative 32 minus 32. That'd be negative 64 w's. And so the 16w to the power of 2 just drops. And also the positive 64, okay? And that's it. That's as far as we can simplify that. So again, this one shows up in descending order, which is nice. Descending order is nice when you start to factor, but right now it doesn't really matter if that is in descending order. All right, here's this one, 6x plus 1/6 to the power of 2. You guys try this one out, then we'll go over it, okay? All right, now I'm going to show the distribution kind of like you would with FOIL. For those of you that I think may prefer a shortcut on this one. It just means that I'm not going to be showing as much work, and since you guys tried it out, hopefully it kind of makes sense, okay? So the distribution, like I said, they kind of show it like this. And again, if there were more terms here, I would just show extra rainbows coming out of that 6x right there, okay? So the first distribution, in fact, I'll use different colors for these. Technology will let me. So I'll start with the 6x times 6x, okay? So that'd be 36x, but remember there was an x times x, so that's x to the power of 2. And then we have the second distribution, that's 6x times 1/6. Now for me, I would just type in 6 times 1/6 in the calculator. It would show me positive 1x's. And yeah, you can make that a phantom one if you'd like. I'm going to keep it there though, because now I'm going to distribute the 1/6. Now some students do it above, some students do it below like this. It's up to you, okay? But 1/6 times 6, again, that's still just positive 1. That's how many x's we would have. And then finally 1/6 times 1/6. All right, said I used a different color, right? There we go. So that's fraction multiplication. 1/6, you can just put that in the calculator, by the way, 1 over 36. And this one's nice because even though this is a fraction and we hate fractions, and perhaps it even causes some anxiety just being there, we don't have any other like terms to combine with that fraction, so it's pretty much done. It's just that we got the x's there in the middle we can combine, right? 1 and 1 is 2, that's positive 2x's. So then we end up with 36x to the power of 2 plus 2x plus 1 over 36. And that would be it right there. So for this one, I'm going to go back to, not doing just lots of rainbows on this one, but actually show what's going on this case. So I'm going to take this x, and I'm going to multiply it by that second binomial, like this. And then I'll also take this negative 7b, and also multiply it by the second binomial. Now, one of the ways that this gets a little confusing for students is that we're going to end up with x's times b's, all right? And some students are like, well, I don't think we can do that. We can, because it's multiplication. You can multiply anything you want together. It's addition and subtraction of terms where you can't do that, okay? Because then they would be considered not like terms. But is x groups of 8b's, yeah, that's fine, okay? So we're going to distribute x times x, well, that'd be x squared. And then x groups of 8b's. So again, I like that number in front to show as a coefficient, but technically I don't think you have to. And then even the order of the letters here, x times b, we can't evaluate that, but we can show it. And remember that these are variables. The letters are supposed to represent numbers. So eventually this I would call a formula, x would be some number and then b would be some number. Okay, so we're just kind of looking at what the final version of the formula would look like. So x and b, you could put b then x, doesn't matter. Okay. But now I'm going to distribute this negative 7b's. And if you'd like to see that 1 there, that phantom 1, that's fine. But negative 7b's times 1x's. So I'd say negative 7 times 1 would be negative 7. And then, so you could say bx right here, as long as you understand that xb is a like term with bx. Because remember, when I said the order doesn't matter, you could commute this right now with the commutative property of multiplication and just say, I'm going to make that xb just so it looks more familiar and then I know to combine those. Doesn't matter. I'll keep it like this just to kind of emphasize the point, okay? And then we got the negative 7b that we got to multiply by the 8b's. So negative 7 times 8 would be negative 56. And then again, it's b times b, or 1 plus 1, which is 2, b to the power of 2, okay? And then, yeah, we got that xb terms in the middle. How many xb's would that be? 8 minus 7 is 1. So then I can drop the other terms. X to the power of 2, that's a positive 1. So plus, and then negative 56b to the power of 2, okay? And just for the sake of being a math nerd, I'll make that a phantom 1. It does make me feel better inside, although I wish it didn't. But there you go. And I believe that Canvas would give you full credit even if you put the 1 right there. But I'm a math nerd. We saw a ton of multiplying letters together, A's, B's, and C's, or X, Y's, and Z's in, what was it, 4.1 when we looked at exponent properties. So now we're seeing that again, just there really wasn't a lot to do with the exponents on that, except for the b to the power of 2 and x to the power of 2 on this one. So just to emphasize before we finish this section, is eventually what we're going to have to do is work this backwards. So we're going to start, we would start with something like this, although they'll start with something a little bit more understandable. And then we would work our way backwards, like we'd split this term up into these two terms, then we'd have these two, and then we look to factor out, in this case, an x, in this one, a negative 7b, and then we split up the 2 into 2 binomials like this. Okay, so right now we're just working pretty much directly downwards with multiplication, but eventually we do what we call factoring, which is just this in reverse. That's it.